along with Dr. UC Dunka sir. And in this, we are going to have first talk from Dr. Joshua Dixon. After that, I would request Dr. Benjamin to please come and finish whatever he could not yesterday. I'm very sorry. Yesterday, I squeezed your talk. And after this, Mr. Sanjeev from TSI, General Manager India, will be presenting, right? So, Dr. Joshua Dixon received his BSc from Old Dominion University and his MSc from the University of North Carolina, Wilmington. He trained for many years as an analytical chemist and worked in numerous laboratories as an analytical chemist and instrument developer before coming to Sunset Lab in 2008. Currently as Vice President with Sunset Laboratory, Josh works on instrumentation development with global operations as well as sales and services. Josh is an expert in carbon aerosol particulate analysis instrumentation and can answer any question pertaining to theory and operation of these devices. So I want to summarize those who missed that this is day 2 of this winter school. Today we are focusing on carbonaceous aerosol measurements. In the first keynote lecture, Professor Neeraj Rastogi elaborated upon the sources, importance of carbonaceous aerosols. Now in this lecture, Dr. Joshua will be talking about organic and elemental carbonaceous aerosol filter-based measurements. And post-lunch, Professor Rastogi will be taking another lecture on instrumentation and analytical techniques, focusing more on how to analyze your sample, aerosol sample, using OCEC analyzer. I also want to state here that in Hari facility, which is called Himalayan Aerosol Research Instrumentation Facility, we are having this OCEC analyzer. Post lunch, we are going to have a hands-on training on that instrument. I always want to remember that we are having a hands-on training program, and in this winter school, we are going to emphasize on that, and we would like all our participants to gain real understanding, as the Chief Secretary yesterday was saying, that we have to have good understanding, and unless we are not doing hands-on, we cannot gain that, right? So now over to Joshua.
Thank you, and thanks for that introduction. And thank you for having me here. I wanted to first say thanks to Dr. Rastogi. His talk, I thought, was fantastic. And for all you students out there that are paying attention, I would highly encourage you to obtain a copy of this talk. How thorough that was very impressive, and what I thought.
So I want to intervene that all the lectures are getting recorded. We are live on YouTube, and all the PowerPoint presentations also we are giving to all the participants in the pen drive.
Fantastic.
So they will be having a question.
All right. Well, his talk leads nicely into mine, and so what I'm going to discuss with you guys today is carbonaceous filter measurement, so OCEC analysis, and some of the options that these instruments have. There's one located downstairs, so some of the hardware and some of the instruments that you'll see in my talk, you'll be able to see one downstairs and actually put your hands on it and see how it works. So let's go ahead and get started. I'm going to go through some of my first slides a little bit quickly so I can stay under 30 minutes. And also, I wouldn't want to, Dr. Rastogi's talk was so thorough, it wouldn't do him justice. So here we go. So where do carbonaceous aerosols come from? They come from combustion. They come from various sources of wildfire, industrial pollutants, engine combustion, domestic heating, and just plain old open burning. The carbonaceous aerosol species that we're talking about are total carbon, elemental carbon, organic carbon, and then there's also black carbon and brown carbon. But the unique thing about black carbon and brown carbon is that they are measured optically. And so that's a big difference. And so we'll talk about that a little bit throughout the talk and what the difference is. First, what is organic aerosol or organic carbon aerosol? We know that it is the product of burning. It's primarily in incomplete combustion. So that's where you get all of these interesting but not necessarily healthy chemicals that are produced that Dr. Rastogi talked about. And what is elemental carbon? That's the core particle of soot or diesel exhaust particle. That is what gives black carbon its black color. Now, I'll talk about it in a little bit. There is a difference between black carbon and elemental carbon. And you'll commonly see them, the two used interchangeably. But I'll make a point in one of my slides that I hope we all take away is that there is a difference between black carbon and elemental carbon. But we also know that it's the product of the carbonization process, the pyrolysis, or heating in the absence of oxygen, or incomplete combustion sometimes. So why is it important? The most important things are that it affects your health, that black carbon and elemental carbon and organic carbon, they affect the climate, and we're coming up with new, or scientists are discovering even more reasons why the effects of these chemicals in the atmosphere cause. So who's using these instruments besides Central University of Germany? People in the industrial hygiene community use OCEC instruments. They like to know how much diesel exhaust workers underground in mines. There was a presenter yesterday that spoke about mining. So people that are working in mines, mine ventilation, that is, if you ever want to quantify and know how much people are being exposed to the diesel engines that run underground, this would be the type of measurement that you would use. Obviously, aerosol and atmospheric research, because that's where we're at such university right now. Regulatory agencies, environmental monitoring agencies, climate change and greenhouse gas researchers, engine emission laboratories, just some of the, giving you guys an idea, and mine operators. We have instruments that are installed in mine ventilation shafts. So sometimes we're measuring the people that are in the mines and what they're being exposed to. And sometimes we're measuring the amount of elemental carbon and organic carbon that is just in the atmosphere in a mine. All right, so past techniques for measuring OC and EC were very rudimentary. I always like to show this device right here. This is a soxhlet extractor. I spent many years of my life operating these. But it used to be a way that we would remove chemically organic carbon from filters, and then we would measure the elemental carbon. And so, or vice versa. Sometimes we would measure the extract, sometimes we measure the filter, just depends. But back in the 80s, a group of researchers at the Oregon Institute of, or Oregon Graduate Institute came up with this technique, and they said, hey, why don't we first heat the filter under an inert gas environment? At the time they used helium, and then switch to a slightly oxidizing environment and burn off everything that's on the filter. And so they said, okay, that should work perfect. We should be able to quantify our organics and then switch to this little bit of oxidative potential in our gas, and then burn off all the elemental. And so they did this analysis for a few years. And then one day the instrument broke down, and it broke down in the inert phase. And so they found out when they opened up the oven, because they were using an organic standard, and they knew that this standard was clear when they put it on the filter, because they just wanted to calibrate. And when they opened the instrument, the filter was black or brown. And so they kind of scratch their head and they think about this and they say, well, why is it brown? We didn't put anything brown in the instrument, or black. And the reason is that the sugar pyrolyzed. And so that's normal. That's what you guys might think when you cook with sugar on a stove. And so, you make caramel, or at least that's what we call it in the US, when the sugar gets brown and dark and after you heat it for a while. It's a similar process. And if you leave it there long enough, it'll turn black. So that's what happened inside this instrument. And so they came up with this method called thermal optical analysis. So it's basically, they do the same thermal analysis that I just described, but they added another component. They added a laser to monitor the transmittance through the filter. And you can actually monitor the transmittance, or you could monitor the reflectance, but you can measure them both too if you want. So here's the analysis. Here's what it looks like. And I'll be as thorough but as brief as possible. So I described first a inert gas phase right here. That is, so if we have the detector and sensor response here on your y-axis, and then time here on the bottom. So this first phase is our helium, or our inert phase. So there's no oxygen present in that gas phase. So it says helium, but we actually, there's a significant amount of people using argon now too. So argon will actually work as well. And then we're simultaneously heating and monitoring the laser. And so I'll show a slide in a minute what that actually looks like. But right here, we see the laser start to go down. And so what that means is that if the laser is flashing on the filter and the color of the filter changes dark, as we learned earlier, black carbon absorbs all radiation. So if it absorbs everything, it's black, it gets darker. And so we find that on certain organic carbons, certain species of organic carbon will thermally dissolve off the filter, and then some will just pyrolyze and turn black. And so we have to account for that, because that pyrolytic carbon, when it was deposited on the filter, when we first collected it, it wasn't pyrolytic carbon, it was organic carbon. So we have to correct for that. And so that's where this method comes up. Let me just make sure I didn't miss anything. So yeah, so one thing to, this is what's happening on the filter in the front oven, but there's a series of other steps that occur downstream. Most notably is that the oven will convert all carbon species. So Dr. Rousseau, you've mentioned that for every carbon atom that's on the filter, it gets converted quantitatively, 1-to-1. So take us back to our stoichiometry classes. For every one carbon atom gets converted to 1 molecule of CO2. And so there's CO2 detectors, there's NDIRs that we use, and then there's also, you can quantify methane. And so we do that through an FID. And there's a second conversion oven in the instrument that's called a methanator. And so that's a pretty popular method. And the instrument that we'll see today has a methanator on it. So you'll see that it has a little box sitting on top with a methanator oven and a small chimney where the FID comes to, or the FID exhaust comes out. So this is what a typical OCEC instrument would look like from Sunset Lab. So there are other models out there, and there's other manufacturers, but this is kind of the basic, let's call it. So it consists of a sample oven, some sort of laser. We use a diode laser. There's helium, neon lasers, and other versions that are available. A back oven oxidizer, something to detect your carbon. So a methanator and an FID combination unit, or an NDIR. Flow control, so you have to control your carrier gases as they move through the instrument. CPU, you got to gather all your sensors and your data that comes from your sensors and put it all together in some sort of software legible, packet of information. And then operating and calculating software. So this is the, I guess you would call it, the fundamental piece of an OCEC instrument. This is what's called the quartz oven. And so what I've highlighted here is the first section of this oven that's in red is what's called the sample oven. And this is where your sample filter sits. And so you'll see it, I have it drawn out right here, but there is a quartz spoon, and that's where your filter sits. And so up here on top is our laser, and it's shining down. And then right here on the second half of the oven, that's our first oxidizer. That's what's going to convert all of our carbon into CO2. And then it proceeds down the plumbing chain, or plumbing line, the tubing, to your detector. Here's a better look, and to give people a better idea of how the optical corrections. Remember, it's thermal optical. So the first image was showing us how it heats and does the thermal analysis, but the optical correction and how our filter sits is right here. So right here is indicating where your filter would be, and it's a small, 1.5 centimeter by 1 centimeter punch that sits right under the laser. You have a optical detection source here at the top that can measure the laser light as it reflects back. So also you hear sometimes a subset of thermal optical analysis called TOR, which means thermal optical by reflectance. And then you have a transmittance detector at the bottom, which is measuring the intensity of the laser as it passes through the filter. And so that's thermal optical analysis by transmittance, or TOT. And so there's various methods available that people have developed, and some use reflectance, some use transmittance. Here's an idea, or here's a slide that kind of explains the idea of what we call in OCEC analysis the split point. And so a lot of people have a little bit of trouble understanding this. So I'm going to take my time on this slide for a minute or two. And if anybody has any questions, I wanted to follow in the same format as Dr. Stowe. Please interrupt me, throw your hand up, call out. Just if there's something I say you don't understand, just please ask. But what happens is right here represents the beginning of the analysis. And so we're proceeding through the analysis, and all of this green right here is your carbon as it's coming off the filter. So the filter is getting hotter and hotter, and then time's proceeding. And then right here at this small step right here, that represents a cool down. The instrument switches over to its 2% oxygen phase. And so these two traces right here, this is the bottom one is your transmittance, and the top one is your reflectance. And what we're seeing right here is, do you see where the lasers, both lasers, they get dark? They go right down right here, and that represents whatever the sample source that's, or whatever the sample that's on this filter, it pyrolyzes. And so we want to know how much of that pyrolytic carbon is on our filter, so that we can assign it to our organic carbon at the end of the at the end of the analysis. So what we do is, and this is the same for all organic or all OCC analyzers, is we use our software and we look backwards through the laser data. And so there's a couple thermal corrections, because not getting into too much detail, but there are compounds that can exist on your filters that are called refractory materials, which means that they don't burn off. And so if they don't burn off, sometimes they can change colors when they get hot, they can irradiate, and you have to correct for that. And so we have algorithms built into the software that know when that's happening. But we look backwards through the laser, and then we say, okay, when does the laser equal the initial value? So the initial, we know what the laser was at the beginning of the analysis. And then we say, okay, when that laser comes back up and it's equal to that same point, that's our split point. And so you might be saying, well, how does that work? And it basically, it's because OCEC analyzers function under a big assumption. And that assumption is this. And if once I explain it to you, I think you'll realize that it kind of makes sense. Pyrolytic carbon. So remember, pyrolytic carbon is essentially elemental carbon. But when we pyrolyze carbon inside the instrument, we're forming elemental carbon in the instrument. But there's nothing in there for that primary elemental carbon to react with. So it's highly unstable. And so when we introduce oxygen, that pyrolytic carbon is highly unstable. So the assumption is it's the first to evolve off the filter, because the elemental carbon that we're actually interested in as scientists came from the atmosphere. It was already stabilized, chemically stable in the atmosphere, reacting with whatever other aerosol species are in the air. And so we assume that pyrolytic carbon formed by the instrument comes off first. And so if that assumption is correct, then the way we place the split point is correct too. Any questions? All right. So next question is, how do we know that this works? It's a great idea, and it has involved a lot of scientists in development. But what do we do to make sure that what we're saying works? So we've done all kinds of method validation, but the most famous one is this one right here, where the founder of our company, a guy named Bob Carey, maybe you guys have heard of him. I know that Dr. Rastogi's heard of Bob Carey. If you guys don't know this, he had the first OCC analyzer in India, and I think it was 2006. Yeah, 2006. He's got an antique, but yeah, Bob came and installed his instrument. But back in the mid 90s, Bob worked with a scientist by the name of Eileen Birch, and she is with a U.S. government agency called NIOSH, which is the National Institute of Occupational Health and Safety. And so they wanted to quantify diesel exhaust. And so they came up with this method, because they knew that they wanted to know they wanted to first collect total carbon aerosol and then speciate it during an analysis and say, okay, how much of that is organic and elemental? And so after they developed the method, they decided to test it. And what they did was they collected a series of samples. And so what they would do is they would have multiple samplers, and they would fill a chamber first with diesel exhaust, and then they would collect a few samples with diesel exhaust, and then they would put some organic carbon in there, so some smoke, whether it was cigarette smoke, biomass, or something like that. So they did this for weeks. They collected a huge set of filters, and then so they had filters that had only diesel exhaust, and then they were overlaid with organic carbon. And so they went through this, and they would have these sets, and they would have a set that was a single elemental carbon filter, and then a single organic carbon filter, and then a combination of the two. And so basically they would analyze each individual one of organic carbon and elemental carbon, and then they would measure the carbon, the combination filter, and compare the results. And then obviously it worked, because I wouldn't be standing here. But they did this over and over again. And there's a paper, I think it was published in somewhere around 98 or 99, that goes through all of this. 96. Oh no, that's the original. The 96 is the original instrument development, but then the method validation occurred a few years later. So let's talk methods. So how does this thing run? What do we, there's various ways, because one thing that people don't tell you until you buy an instrument is that there's no accepted standard for elemental carbon. Elemental carbon is, it's elemental carbon. It's inert. It's very hard to work with. And I mean, just think about the fact that the only way we get it off of a filter is by heating it to 700 Celsius and then putting oxygen in there. Which, you think about it, if it was more than 5 or 10%, would be a little crazy. But we're able to oxidize it all off. But what we do is we have these 3 methods, or kind of our most popular methods, let's say, that are used throughout the world. The first is NIOSH, the one that I discussed, NIOSH 5040, and that just refers to the manual number. There's another one called USAR2 that was developed in Europe. And then there's another one called Improve-A. And Improve-A is a unique one because it uses reflectance. And so the scientists that developed that one thought that reflectance gave them a better value and a better understanding of what was happening on the filter. We've always kind of said, it's one of those things, we don't necessarily support one or the other. And so we just provide the ability to do both. The one unique thing about Improve-A is that it was a measurement developed around not chemical speciation, but it was around the visibility and aerosol visibility. Because what happened was back in the 80s, when the US had pretty bad air pollution issues, people were showing up to the national parks there, and the US is very proud of our national parks, and you couldn't see the view. And so they came up with this air quality network to monitor the national parks and all the visibility there. So it's a very old, I think it's probably upwards of 30, 40 years old now, and there's about 30 years worth of monitoring data out there using the Improve-A analysis. So how do we do it? How do we collect our samples? How do we get them in the instrument? How do we get our numbers? The first way we start is with quartz fiber filters. I think you guys have a Tish, but this is a URG sample collector. There's numerous options out there. There's numerous ways to set these up. As Dr. Rastogi described earlier, there's different sizes of organic aerosols and elemental aerosols. So the way you construct your inlet will dictate what you measure. So if you want to measure small aerosols, you set up your collector to collect small aerosols. You use things like a cyclone or a dicot, which are various types of inlet sizing devices. But you use a quartz filter. They look like this. Some of them look like this if you're in a different field. This would be what a lot of industrial hygienists use. These are smaller and they kind of fit on a respirator. But essentially, at the end of it all, you get these little filters like this. Well, sometimes big filters if you're using a highball, and you take a punch out of it and you put it in the instrument. And so that's what that looks like. So right here is just a close-up of somebody putting a filter or actually it's a white filter. So I assume they're taking the filter out. They've done the analysis, because if they hadn't analyzed it yet, it would be black or brown. But before you put it in, you have to take a small punch of it and put it in the instrument. So you perform the analysis, and that typically, this is, at least with some set instruments, this is what the data looks like, or at least the operating software looks like. After the analysis runs, you're able to look at that data. And so this is our second software that accompanies the instrument. That's called our calculation software. And so this is just giving you an idea of the results for each individual analysis that you perform. Some people like to know how much carbon comes out at specific peaks, or I'm sorry, not at specific peaks, at specific temperatures. They like to manually integrate values. These offline instruments that I'm describing right now can actually, there is a passive way to measure inorganic carbon. So if you were ever interested in carbonates, so carbonates are pretty large, so you would have to at least use an inlet that could collect probably PM10. But you can actually do that. It's a little bit more time intensive, and you basically do what's called an acidification, because carbonates will dissolve with acid, and you run 2 filters, and so you can do a difference measurement. So you can see there's more information up here that I won't go into too much detail about, but I always like to show people what it is that they're looking at. And here's an even, and after you're done with the calculation software, you actually get tabulated results. And so this would be, all of these results would be the product of somebody operating the instrument doing one analysis at a time. I plotted up some of the data just to see, so you guys can see what it looks like. There's a mention in the previous talk about EC-TC ratios and OC-EC ratios, and so that's where this kind of ties into source apportionment. It doesn't, these instruments, they don't have the resolution of an AMS. You're not going to understand, oxidative potentials and look for specific fragments of molecules inside your aerosol, but you will get a rough estimate of some of your source apportionment in carbon. So you'll know that EC, as we talked about earlier, is the product of combustion, of complete combustion. And the only thing that combusts completely are engines. And so we know that that's, or let's say anthropogenic combustion sources. So when we have high EC signatures, we know that there is a high contribution from humans. And when we have higher OC signatures, we know that not necessarily. Something I wanted to talk about as well is because OC-EC can be done online. So there's an instrument available that you can set up that can run in real time. And so these are devices that are unique where it actually performs, it does the filter collection and the analysis at a specific location. So the other unique thing about these instruments is it simultaneously does a real-time black carbon. Here's a quick overview of what an online instrument would look like. Just showing here a brief kind of caricature of a human in a sampling shelter, and then this would be what the instrument itself looks like. So you have flow through right here. You have a laser flashing, and as the instrument does its collection. Typically, when you set up something like this, you need an inlet, you need water traps, a parallel plate organic denuder. That would be something that you can use or not use, because an organic denuder would allow you to select or selectively remove VOCs from your sample. So if you wanted to have VOC signature on your OC-EC, you could leave it off. But if you wanted to remove it, then you could install that. We always use a PM 2.5 cyclone, but you can use other cyclones on these devices as well. So this is what the analysis looks like from an instrument like this. You'll notice that this looks strikingly different than the instrument downstairs, but the instrument you can program it. So, if you want 30-minute OC-EC resolution at a specific site, you can program this instrument to run every 30 minutes and give you a OC-EC value. Please go.
Is it also required gases like helium?
Yes, it does require gases. Yeah, if you're going to do OC-EC analysis, you have to have an inert gas supply, and you have to have O2 supply. There is a way to do what's called BC-TC analysis, where you measure black carbon. So recall that this instrument will do black carbon. We'll do black carbon, but if you're going to do OC and EC, and I'm going to discuss in a second the difference between OC and EC, then you have to have the gases.
Both in online and offline mode.
What's that?
Both in online and offline mode.
But yeah, you can actually, there is a way to calculate black carbon on the offline measurement as well. I'll show you. I might have skipped over it. There you go. Okay, so it's really small, but there is a column in our data that's we call it optical EC, and I'll tell you in a second why we call it optical EC. But there is a way to look at your black carbon on an offline filter measurement, and all that is just the measurement of the initial absorbance and the final absorbance. So how do we measure black carbon on an online instrument? And actually, how do we measure? It's all the same measurement. All you're doing is measuring the change in light absorption of a filter. And so some black carbon instruments use Teflon filter, some use flow through, we use quartz filters. So they're highly scattering, so we have some corrections that we have to deal with that. But basically what happens is the instrument's collecting the OC-EC sample. What we do is we monitor the filter every minute. So it's collecting, so let's say there's a 30-minute collection. the laser is monitoring the filter as it changes. And so remember, black carbon is basically light absorbing particles. And so as that filter gets darker and darker, we calculate the change in absorbance every minute. We use something called a mass absorption coefficient. And this is kind of a unique value. One of the things about black carbon, and Dr. Rastogi did a really good job of describing it, is it's very unique to every location. So it's source specific is what they say. And so mass absorption coefficients for black carbon vary. So we, at Sunset, we understand this. And so one thing we like to do is we have our default mass absorption coefficient. We are born of diesel exhaust analysis, I guess would be the right way to say it. But our mass absorption coefficient is calibrated to diesel exhaust. But we understand that out in the environment, it isn't pure diesel exhaust. It's the amalgam that is, or atmospheric aerosols. It's everything. So you have to look at that on a case-by-case basis. And so we provide you with the ability to apply your own determined mass absorption coefficient. So let's talk a little bit about elemental carbon and black carbon. What's the difference? Why are they different? So the first is elemental carbon is pure elemental carbon. It's black graphitic carbon, just like Dr. Rastogi described to us earlier. What is black carbon? Black carbon, it is the cumulative measurement of all aerosol that absorb light on that filter that we collected. So everything in there that might possibly absorb light. So, and if you think about it, that could also be organic brown carbon. There's plenty of metals that absorb light that we might find in the atmosphere, and it's measuring all of it. And that's what makes that mass absorption coefficient of black carbon unique. It's an optical, black carbon's an optical measurement, and elemental carbon is a chemical measurement. We're measuring carbon. The one thing I always say, the difference between a black carbon analyzer and an OCEC instrument or organic carbon, elemental carbon instrument is that at the end of the analysis on an OCEC instrument, there is a detector that physically measures carbon.
Does other metals include the process of measurement of black carbon?
I'm sorry, I couldn't hear you.
I request to use the mic because it is for benefit of all.
So does the presence of other metals hamper the process of measurement of black carbon?
Very good question.
Because
Yes.
it's based on optical and, as you said, the thermal
Yes.
signatures.
It does. And so here's how it interferes. So what do metals do when they're put into the air? They oxidize. What is the principle of an OCEC instrument? It's to control oxidation until you want oxidation to occur. So if you have a filter that has a high amount of any metal oxide, I usually use iron oxide because everybody knows rust. But if you have iron oxide on your filter, you have a source of oxygen. Now, that oxygen is tightly bound in a chemical bond between iron and oxygen. But as we all know from our physical chemistry classes, you give anything enough heat and something's going to happen. And that's what happens. Our instruments get really hot, 700 Celsius, 800 Celsius, 900 Celsius. And when you have any oxygen present, maybe I can't think of an example that doesn't actually provide oxygen as a source of oxidation at that high temperature, but especially rust. So if you've got rust on your filter, then you'll start to do what's called pre-oxidation. And so that's a term that Sunset made up. And so pre-oxidation means exactly that. Oxidation is happening when we don't want it to occur. And so with single analysis filters like the offline, the issue isn't that big of a deal. I mean, unless there was like a dust storm and the amount of iron oxide in the dust was extremely high, then you wouldn't really worry about it. Because the other thing we have is we have algorithms that look, you can actually see the laser change as it gets hotter. So remember that OCEC instruments cool down. And so when they cool down, you see the inverse of these metals cooling and interacting with the laser. So you can basically use some fancy math and determine those effects on the filter as it's heating. So heating on the filter, it's not a symmetrical, I guess, relationship. But as it cools, we've spent some time determining that. And so now we can model and do what's called a thermal or an optical correction. Not to be confused with the optical correction of a split point, I know that's a little confusing, but we do an optical correction of refractory materials, and so you can correct for that, and it's pretty easy. But yes, very good question.
Another one is that at 700 degrees, is there any carbon species that get evaporated that we lost in the measurement?
Is after 700?
Yes.
It depends. So there's your statement right there is why there's an improve A, why there's a USAR2 method, and all the methods that exist. Everybody has slightly different thoughts about what is happening from that 550 to 870 range in the inner environment. And so NIOSH, NIOSH is a very interesting method. So if anybody is really involved in this, I would highly encourage you to read the method because it's ambiguous to a certain degree. And the reason is because they know, well, they being Bob Carey and Eileen Birch, the principal scientists on the development of that, they knew that oxidants can be present in your filters sometimes. So NIOSH, everybody assumes, just goes to, you set to the 870 at the high point. But it actually says in the method, it can go anywhere from 750 to 870. So you can modulate that temperature that if you were to accidentally, or not accidentally, but if you just, your samples happen to contain a lot of oxidants, you just lower the temperature and proceed. All right, let's talk about BCTC analysis because this is kind of a new analysis that's come on or come into vogue in the past 10 years. And so this is black carbon and total carbon. So let's exclude the OC and the EC and just measure black carbon. And then the one nice thing about the BCTC analysis is one, you get to see black carbon, which is, you know, the profile and the optical characteristics of the black carbon on the field as you're collecting it and as it exists in the actual aerosol environment versus EC, which is stripping out the OC and looking only at the core particle. But what it allows you to do is collect a lot longer. And so if you wanted to get really long, high resolved black minute profile or black carbon minute to minute profiles of where you're collecting, then this would be what you did. But if you wanted to know your organic carbon truly, because remember, and I guess it's the questions that you ask, because remember, there's going to be some organic carbon. Remember those structures that Dr. Rastogi showed us of the black carbon and those lacy structures and all of the organic carbon that would surround an elemental carbon like kernel or nucleus, depending on where you're from. Some people call it different. That would be included in black carbon because that's part of the light absorbing, I guess, characteristics of those particular aerosols. Now, if you do an OC-EC measurement, that OC that surrounds the black carbon gets burned off. So it's all a question of what you're looking at. The nice thing is if you're running the OC-EC instrument, the online instrument, you get all of it. So you get OC-EC, elemental carbon, and black carbon in 1 minute black carbon profiles. The only trade-off is you have a much longer analysis time. So you have between, you know, for every time you do a collection, you have to wait. I think it's anywhere from 15 to 25 minutes, and that just depends on the OC-EC method you choose to use. So here's an example of some of the results. I probably should have flipped to this a little bit earlier, but this is the online. And so you see we get OC, EC, OC by difference. That's just total carbon minus black carbon. So BCTC, that's a value that you see in literature now, depending on, there's another instrument by McGee that does BCTC. And then various other parameters. I always like to show this. This is OC-EC being measured. We set up an instrument in a mine. So, I mean, where are you going to get higher elemental carbon values other than down in a mine where everybody's driving, diesel vehicles? This is basically every. We're doing an OC-EC analysis twice an hour, and just following the profile of the aerosol for three consecutive months, just never changing the instrument, and just monitoring all of the changes in shift. So you can see you get profiles of, when workers are at their height of working, when they take off for the weekend and go home. Sometimes, it's a mine, so they have to blow things up. They have to blow up the stone so they get their stone. So you see even higher signatures when they have what they call blasting days. It's a very interesting data set. But then, if this might look similar to what we just looked at, but this is actually 1 week. And what we're looking at is 1 minute black carbon profiles. So it's a really cool thing that you can do with an OCEC online instrument is you can, one, say, okay, here's my OC, here's my, or, for my 30-minute collection, here's my OC, here's my EC, my TC value, and my black carbon cumulative value. But then you can also open up your black carbon and see exactly what was happening on a minute-by-minute basis. So you get this really interesting resolution. And if you, depending on what you're looking at as a scientist, you can distinguish and determine different things that are occurring. So I think that kind of brings me to the end. I hope that kept me in 30 minutes. And if there's anybody who has any questions, I'd be happy to answer.
Yeah. Thank you so much, Dr. Josh. I think we will take questions at lunchtime.
All right. Well,
Now I request Professor Neeraj Rastogi sir to honor the speaker. Thank you so much, sir. Thank you, Dr. Josh. Now I will request our next speaker, Dr. Ben, for elaborating upon what he couldn't do yesterday.
इसमें नहीं लगी